So this week we're talking about environments of deposition that occur in association with the ocean or the marine environment. So we're talking about coastal environments. So here you can see beaches, coastal dunes, we've got reefs, and we're also going to talk about what happens when you get farther from the shore, so the deep ocean as well. We've talked already about river deltas, but we'll bring them up again because that's an important source of sediment. So the areas that we're talking about include the coast, which is, right here along where the water meets the land. But also we'll see a significant and important area of deposition is going to be the continental shelf, and then also what's called the continental slope and rise. And if you look at this side view or slice that goes through this area, you can see that we are definitely going to be depositing sediment right up here by the shoreline. That's where we visit. That's what we think of usually. But you'll notice there are some very, very thick layers of sediment that occur offshore. And as long as we're near the continent, we can accumulate significant amounts of sediment. And ultimately, this is where a lot of our sediment is headed anyway. So if you think about river systems, rivers ultimately bring things to the coast. If you think about glaciers, the meltwater then turns into outwash, and that takes things to the coast. So most of the environments that we talk about, the sediment ultimately will make it to a coastline and become perhaps marine sediment. The other thing that's going to be really significant will be the deposition that occurs on the continental shelf, not only along the lines of what we've been thinking about so far, which is kind of pieces of rock that are being washed toward the shoreline, but we'll see there's a significant role for animal life, making their shells and creating limestone, which is one of the, if not the most common type of sedimentary rock that we find. So anyway, let's start to get into it. Let's see what happens at the coast. If you go to the coast, one of the first things you'll notice are waves. And so there are a series of slides that we're going to look at. First of all, talking about waves. And one of the things that you'll notice in this slide is the motion of the water in the wave. And we'll have another slide that kind of looks at this again because it's important. The water in a wave on the open ocean moves in circles. We call these waves of oscillation. So the water oscillates. The wave form moves, but you'll notice that the water returns to its original position as the wave goes by. That's what these circles are trying to show. The other thing that you'll notice is that these circles get smaller as you go deeper. So at some point, we reach what's called the wave base, below which there is no appreciable action, which means that the waves and the work that they do are going to be focused in the upper part of the ocean. And in terms of moving sediment around, there's not much happening in this picture because the waves and the moving water are not in contact with the ocean floor, which is where most of the sediment is. So it's important to know some of the terms. We've got crest and trough labeled on here. The wave base, which we talked about on the previous drawing, is 1/2 the wavelength. So if you measure crest to crest or trough to trough, that gives you the wavelength. And the depth of water motion is equal to 1/2 of the wavelength. So here's our picture again. So that just gives you an idea of where this work is taking place. So really where we see the waves doing a lot is as they approach the shore. And in order for them to do significant work, you really have to have a water depth that is less than 1/2 of the wavelength. So again, the message here is that most of the work along the coastline being done by waves is happening in shallow water, basically where you can see it. So what do we see the waves doing? Well, they can do some erosion. So you'll find features like sea cliffs, caves and sea arches, pinnacles and sea stacks, and wave cut platforms. And the wave cut platform is something I like to point out because if you look back at this previous slide, you will notice that the waves have a wave base, right? We just mentioned that. There's a maximum depth at which they'll work. And even if you're at half the wavelength deep, you'll notice there's not really a lot of motion going down there. So most of the work is even closer to shore in shallower water. Well, what this does is it gives us this wave cut platform because there's a maximum depth to which the waves can work effectively. And if you look at the picture with the pinnacles and sea stacks, you'll notice that they're sticking up off of a relatively flat surface. And again, that is related to the maximum depth of wave motion. The other thing to keep in mind is that the waves themselves can do some work. So if you get hit by a wave, there's a significant amount of pressure there. But they're even more effective once they pick up some sand. So just like with glaciers and with rivers and moving water in the wind, when small rock particles are picked up, those small rock particles, as they're moving, can do a lot of work in terms of physical erosion. So, what we think of more often when we think of the coast, we might think of sea cliffs, but we're much more likely to think of the beach. So here we can see a lovely picture of a beach. You'll notice the waves. I should point this out. On the left side of the photo, you really can't even see the waves. On the right, you can, because as the waves approach the coast, what happens is they stack up. Those circles, in order to accommodate all that motion, the wave gets taller to kind of keep that full stack of circles. At the same time, the wave slows down a bit, so they start to catch up to each other. They get closer. And the top of the wave, because it's not interfering with the bottom of the ocean, is able to move a little more quickly, and it gets in front of the rest of that stack of circles, and it tips over, creating a breaking wave. And you'll notice this stuff all happens relatively close to the shore, and you can see that reflected on this photo. Running kind of up diagonally through the center of the photo is the beach. So that is where the sand in this case is being moved around. And the size of the material generally relates to the energy available in the waves. And so usually we get material that is sand size. On some high energy beaches, we can get some larger particles. Generally speaking, we don't find anything smaller than that. The silt and the clay, the fine particles, we'll see what happens to them a little bit later. But as long as the water's in motion, that material will tend to stay up in the water, and it will end up getting carried out into deeper water. Now, you might think of the waves as going back and forth into and out of the shoreline, but we're going to see that that's actually not exactly the case. If we look at this picture, this drawing from your book of a coast, you'll notice up here we've got the sea cliffs that we mentioned. Here we've got river delta that we've mentioned. These are places that are bringing sediment to the shoreline. Once the sediment gets to the shoreline, it turns out that the waves are able to move that sediment around. So we get transport along the beach, and it's a process that we refer to as longshore drift, or littoral drift, it is sometimes called. And the way that it works is that the waves, it turns out, don't come straight in. They typically come in at a bit of an angle. You can sort of see this here if you know what to look for. You'll notice the wave front is not perfectly parallel to the shore. And so when we look at this up close, the result of that is that the wave pushes the sand in at a bit of an angle, and then the sand goes almost straight back out as the water runs down the beach. So you end up with this kind of zigzag pattern where the sand starts in one place and ends up somewhere else. And this is extremely important shaping the coast because it's going to pick sediment up from places like river deltas and cliffs and move that sand along the coastline to new locations. And here you can see a place where a river enters the ocean, but it's blocked by sand. So this river's dumping a bunch of sand. And then the longshore drift is picking that sand up and moving it along the coast. And in this case, we can actually tell the direction of longshore drift because you'll notice the sand is kind of building up along this barrier, and it's being removed from this side of the barrier and taken in that direction. Here, it might actually be coming toward us, so it can go in a couple directions. But longshore drift is what is spreading out the sand here and creating our beaches. So what happens next? Well, what happens next is some of that sand is moved offshore in what we call turbidity currents. So turbid water is simply a term that we use for muddy water or water that has a lot of sediment in it. And in this case, you can see that the water disturbing the sediment creates a cloud of sediment-filled water, and that sediment can then move farther off the shore. In addition, once we get into deeper water, the finer materials can settle out. That's also going to give us some muddy or turbid water potentially. And this is how we then can move some sediment out onto the deeper parts of the continental shelf and kind of spread the material around. This slide shows us the East Coast and the Gulf Coast of the United States. You'll notice there's a relatively wide continental shelf. Our continent actually ends pretty much at the edge of the continental shelf, and as sea level rises and falls, different parts of that shelf will be exposed. But for what we're looking at right now, which is sediment and where does it go, if we look a little bit more closely at the continental shelf, we see this broad flat area. You might remember back early in the slide presentation, this is what it looks like from the side. You can see there's some thick layers of sediment. Now, some of those are from when sea level was lower, and that was the shoreline, and so we built up some sediment then. But the other thing that's going on here is this turbid water is actually taking material out onto the shelf and filling in that as well. Furthermore, you'll notice that there's a little canyon in our continental shelf here, and that gives us a clue as to what can happen if you focus the activity of this turbid water. If we look at the shoreline of California, this is in the Monterey Bay area, you'll notice that there are really like river networks going from the edge of the continental shelf out into the deep ocean. If you dive down in there, what you find is this muddy water. Muddy water is more dense than clear water, and so the muddy water can actually run along the bottom of the ocean as an sort of an underwater river. And that's what carves up the edge of the continental shelf. You'll notice there are actually even kind of meandering rivers down there. And this will take sediment out into the deeper parts of the ocean. Now, once it gets out there, this tends to be finer material. We get deposits that look like this. They're kind of stripedy. If you look at them very closely, what you would find is very coarse sediment up to fine sediment. Coarse to fine, coarse to fine. And that really tells us what happens with this turbidity current. As the water slows down, the coarse material drops off first, and the fine material ends up on top.